Thank you. Thank you, Abdulillah. So can you give me an example of something autonomous but not flexible? Yes, Abdullah.
Something like maybe a car manufacturer, maybe because they can autonomously make cars, but they can't really make anything else.
Excellent. So that does not require human input because it's fully automated, but in the end, it doesn't have much flexibility. And if we want to give an example of something flexible but not autonomous, maybe some programmable controllers, in which you need to reprogram it every now and then, but you still need that human interference. If you want something fully autonomous and flexible, then you can think about advanced robotics, in which you have a robot that is autonomous that takes some decisions, but at the same time it has some flexibility because you can still require it to do multiple tasks. Yes, Mohammed.
دكتور, what can we say about the machines in the زي اللي في المصانع مثلا اللي تسوي bottles والاشياء دي؟
Okay, these are autonomous machines, but they are rigid. They're not that flexible. So you can think about, let's say, a robot arm that does one job in a factory. That's an autonomous, inflexible. That's an inflexible machine. Okay, but let's say you add مثلا certain chips to it, and you add some sensing elements to it, and you require it to do multiple tasks. Then it becomes an autonomous machine, and also flexible. So these two words, I wouldn't say like it's binary, 0 or 1. I mean, there is some gray area in between, but we generally say something is autonomous and intelligent if it can act rationally and independently, and if it has some flexibility. Actually, there is a course. It's a new course, CIC 400 course. It's called Autonomy and Decision Making. It's not offered yet. It might be offered next year. And that will focus, it's an intersection point between really control and industry engineering, because it will focus on intelligent agents and how these machines can act rationally and automatically. So it will focus more on decision making under uncertainty, things like that. And over there, you will see a big intersection between what you see in other industrial engineering classes and this control class. However, in this course, we will focus on single input, single output control systems. But I just wanted to give you this picture and just to have a chat about these general ideas and trends. And there is a course, CISE 483. It's called AI and Machine Learning for Robotics. And it mainly focuses on really intelligent systems. And that, in the context of that course, the intelligent system is the robot. But the ideas are generalizable. Like we focus more on the theory there. And then we give some examples from robotics. Any questions or comments? Okay. So every component or a process can be represented by a block. So we use blocks a lot in this course. You have some input or a cause, and you have a process or plant. And you have an effect or output. The cruise control example is a single input, single output system, but you can have multiple input, multiple output systems, single input, multiple output systems, multiple input, single output systems. You have different variations. The open loop control system utilizes an actuating device to control the process directly without using feedback. Can you give me an example of an actuator? Yes, Abdullah.
Maybe something like the lights switch.
Light switch. So the light switch, you have a button, so that's an on-off decision you make. What is the actuator? The light switch, you mean?
Yes.
I see what you mean, but in this context, we're referring to something else. We're referring to something like a valve, where you, let's say, you have a signal and the valve opens a little bit to increase the flow. Because there is some continuity in the process. For the light switch, you're thinking on-off. Here we focus more on, let's say, continuous devices. Yes, Mazen.
Like brakes in a car.
Brake in a car. Okay, what about the brake?
It acts as an actuator.
Yes, or like what Faisal said, the gas pedal. Yes, these are good examples of an actuator. It can be also, let's say, a motor. Yes, Hisham.
Like a pedal of a car.
Yes, yes, that is correct. Yeah, these kind of devices are actuators. Okay, so so what we have here, we have some desired output response, some number that we give it as. So you'll have, let's say, an entry pad, or let's say a knob, or or let's say a computer in which you put that number, and there is a device that takes that action. Okay, and then it goes to the process or the system or the plant, and then you have an output. There is no feedback here, so it's a one-shot system. You just take the action once. Now, if you have a closed loop system, then you have the measurement of the output, and that measurement is fed back and compared to the desired output. So you have a comparison element, and you have a controller, and you have a process, and you have that measurement. Okay? So the controller here can be an amplifier, for example, and that goes to the process. Notice here, you just have one number entered to the actuator. Here, you have continuous updates, and you feed the error to the controller. So the controller tries to correct the system given that error. Yes, Faisal.
Doctor, the comparison will be at the measurement element, right? So at the actual output will be compared to the desired output.
Yes, so after you measure, you have a comparison element.
Okay, okay. Yeah.
It can be it's a summation node, really. So it's the input minus the output. That operation is the comparison. And that goes into the controller. You can also have disturbance in the system. So notice here, the entire discussion, we're assuming that we know the plant, we know how the system behaves. Okay, and we can actually measure the feedback. But there will be noise in the system. There will be some variation, so the model we will have is not going to be perfect. So you can have also some disturbance into the system. So that disturbance, you can assume it's noise. You can assume that you have some disturbance so that you can capture the error you have in the modeling. And then you can also take that into account, the disturbance, in the design of the proper controller. You can still do that. Actually, there are some branches within control that specialize into dealing with disturbances. If you generalize the same idea, disturbance is really. Do you know what random variables are from statistics? I think you took that in ISE 205. Can somebody tell me what a random variable is? Did you hear the word random variable before? Yes, Mohammed.
Set of variables that affect the main thing we want to test, and also can be, for example, we have a sample. The students are, for example, the random variables. Maybe their scores like this.
So does the random variable have a distribution?
Yes.
Okay, so it is a variable in which it has a distribution, and it might have, let's say, a time element, and we call it a random process, right? So you can imagine that the disturbance is a random variable with a certain distribution. And then that distribution, you can assume it from the knowledge of the system or some previous experience, or at least, you know, like having a system with some disturbance and some random variable is better than designing the controller. If the controller is guaranteed to perform under that disturbance assumption, it's better than, let's say, having a controller and assuming there is no disturbance at all. So one possibility to capture the disturbance is assuming that it is a random variable. For example, it can be a Gaussian random variable, but you can have different assumptions in that. So here in this course, we will talk about disturbance briefly sometime in the middle of the course, but really the focus here in this class is about the entire process for single input, single output systems. So if I want to design a control system, what are the steps? Can somebody just give a description of the steps for designing a control system? Now we talked about single input, single output systems and the main idea. Can somebody tell me briefly how to design a control system to, let's say, give a desired output or a desired outcome? Yes, Yasser.
I think firstly we need to determine what's the input that we have. Is it single or multiple? Then what's the process that we want to control? Then the objective or the output. Also, we need to determine is it linear or non-linear, open or a closed loop system.
Excellent. So you need to determine the variables, the input and output variables, and the kind of control, and the kind of feedback, the kind of control loop you need. Is it open loop or control loop or closed loop? Anything else? Okay. So we have different steps for designing control systems. They are similar to what Yasser just said. So you need to establish the control goals. For example, a certain speed that you want. Then you need to identify the variables to control. And then you need to write the specifications of the system, or let's say the desired performance that you need. And you need to establish the configuration and identify the actuator, because physically you need some device to implement what you need to implement. And you need to obtain the models for the process, for the actuators, for the sensors. You need to capture the mathematical relationship of the system. And then based on that, you can describe the controller and select the parameters to be adjusted for the controller. So if I have a rotating disk as an open loop system, this is an example of what you have. So you'll have a battery, you'll have some way of setting the speed in the circuit that can be resistance, and then you'll have an amplifier that will translate that signal, amplify it to a proper speed for the turntable. And then you have the motor. So you have a desired speed that is actually voltage, but that voltage can be small, so you would need to amplify it in order to really run the actuator, which is the DC motor. And then you have the turntable that will rotate. And then you measure the speed. This is the open loop system. So tell me some drawbacks of this design, and also tell me if I add a feedback, what do I need in terms of devices? How can we close the loop and run this turntable at a desired speed? Yes, Mohammed.
Regarding how to add, how to close the loop, multimeter are usually used in the circuit to measure things, maybe. If you
So
want
the
certain.
multimeter, does it measure the speed?
Oh no, no, sorry, it's a measure voltage and stuff. No.
Okay, so you need some device to measure the speed, right? And then what happens? And then you compare that to the desired speed. And then instead of sending the desired speed to the controller directly, to the control device or the amplifier directly, you will send the error, right? And that error signal will keep adjusting the system. So this is what happened when you add feedback. You will have a tachometer, which will measure the speed. Okay, this is your sensing device, and it will send the voltage signal to the summation node. That will be subtracted from the desired speed, the voltage, for the desired. Notice here that we're subtracting voltage from voltage, so you need these units to match, and you will have the error. The error will go to the control device, and then you'll have the actuator, and then you will run at that desired speed. So if the turntable was not moving and your desired speed is, let's say, 100, then for the open loop system, in the beginning, it will run and then you have no way of tracking it. But then if it goes to 50, and then the error will be 50, so that will be amplified and it will require, let's say, more speed. Until the error diminishes or it becomes negative, then you might slow down. And then you will hit the actual speed that you need if you have proper control design. Okay? And that amplifier is one example of a control device, but you can have different kind of circuitry to design the proper controller. And each design will have some guarantees. So if you know the mathematical model for the process and for the DC motor and for the sensor, and you know your desired input and your desired and the actual output, then you can capture all of these relationships, and you have some mathematical way of designing the controller such that you ensure that the system gives you the performance you need. Maybe it will not, but at least you'll do the best you can do. Okay? Any questions so far? This concludes the introduction part. There is a homework that is just posted this morning about this introduction part. However, because some of you don't have the textbook yet, so I will update it, maybe change the questions such that you have access to the questions you need to solve. And I will update it today, inshallah. Okay. If you don't have questions about this part, then we can move to the next unit of this course. And I'll give you 2 or 3 minutes to take a break before we move to the next topic. So we will start after 3 minutes. I'll set the timer right now, and I'll be here if you have any questions. Yes, Abdullah.
Doctor, can you upload the next slides now?
Slides. You mean the new ones?
Yeah.
I can do that, but they will not be that updated. But sure, I can upload whatever I have, and then I will update it later. Sure. Okay, we're back. So I just uploaded the new set of slides for modeling mechanical systems. And I also, let me just show you what I have. So I'm going to share my screen. Do you see the screen? Hello, do you see it? Great. All right. So this is the student view. If you go to course content, you will see homework 1 posted. I will update these questions, maybe change them so that you have access to them. You will also see the, whatever I presented up to today is posted there. Then you will see modeling mechanical systems, which is the next subunit, let's say. And then you will also see the handout, the first handout that we have for modeling mechanical systems, which we will use for the next, let's say, 2 lectures. Okay? So this is the reference that we will have for this part, for modeling mechanical systems. If we go to the syllabus, I'll show you the syllabus real quick. You see that we have introduction to control systems, and then we have modeling of dynamical systems for mechanical, then electrical, and then solution of ODEs and transfer function. That will take us about 2.5 weeks. So we will talk about it briefly today and continue the discussion for the other 2.5 weeks. So I'm going to share the slides right now for modeling mechanical systems and start the discussion about it. Any questions so far? Okay, again, just a small announcement. Usually, whenever I present, I observe some changes that I want to do in the slides, so I update them quietly on the blackboard. So in the blackboard, slides are updated from time to time, even after the lecture. But usually these are not major updates. And again, for every slide, for every set of slides, you will have the reading assignment, which tells you exactly what is the reference that we will mainly use for that set of slides. Okay, so far we talked about control systems, the idea of single input, single output. We mentioned that control, this process of having a desired objective or a desired performance, and then measuring the actual performance, and then comparing the desired with the actual output, and then taking a corrective action, and that is taken automatically. And adjustment is done to the system automatically. But all of these relationships, we capture them through mathematical models. So it is important. So before you design a controller, you need to have access to the system model. And in this unit, we will talk about modeling some simple mechanical and electrical systems. And then we will talk about how you go from this modeling phase to until the end of the course, until you can actually properly design a controller that gives you a specified performance. So modeling does not need to be from physics. It can be data-driven. And this is where data-driven techniques come in. You can use deep learning to come up with a model, and then based on the model, you design the controller. That's fine. Here in this course, we will focus more on physics-based modeling, just to give you a flavor of the modeling aspect. And again, in control, we deal with dynamics, and by dynamics, I mean things that vary with time. And when you have things that vary with time, usually you have ordinary differential equations. And these differential equations sometimes can be complex to deal with. Imagine if you have an optimization problem and you have a differential equation in the constraint set. That will complicate the problem a little bit. So we will have some techniques to deal with these ODEs, or ordinary differential equations, that are different from Math 208, but they will make things easier for us in this course. So the objective of this unit is to derive mathematical models. These mathematical models are ODEs, or transfer functions, which we will define later, of simple translational mechanical systems. So what is mathematical modeling? Mathematical modeling is really the first step in designing a control system. And once you do that, you obtain a set of equations that describe the behavior of the system. There are two approaches to modeling. One is you do actually physics-based modeling, like what we do in this course. The other one is use system identification using data. If you think about, let's say, machine learning, it falls into this category of identification. It's different words, but it gives you really the same thing. Is it clear so far?
Yes.
Okay. All right. So first, let's talk about displacement, something you know from Physics 101, which is defined as the change of position from one point in a frame of reference to another. So you have a reference point, and you have some change in the position from that reference point, call it R, to another point here, call it B. And displacement is really a vector. And it's a vector quantity, so you have a direction and you have also a magnitude. So you need to specify the reference point and the positive direction, so that this direction, if it's, let's say, along the same direction as the reference direction, then that's positive. Otherwise, it's negative. Also, you need a reference point so you can measure the magnitude too. So the reference point helps you in identifying the magnitude and direction of the displacement, which is a vector. Distance is the scalar quantity of the displacement, which is the magnitude. So distance is the magnitude of the displacement, but displacement gives you more information because you have the direction along with the distance. So for this example, what is the displacement and what is the distance? Can somebody tell me? Yes, Mazen.
The displacement is 1 unit to the right,
Okay.
and the distance 2 units up, 1 unit right, and 2 units down.
So you have distance of 5, displacement of 1.
Yes.
Right. Good. Yeah, I mentioned something that's not correct. I said the distance is the magnitude of the displacement. It's actually wrong. It's not necessary because of this example. Muhammad, you wanted to say something?
Yes, displacement. We need to see the change. What's the final thing? We are one step to the right, but per distance, we may go 100 miles and then come to the same position again. There's no displacement.
Correct. So for the displacement, you have a starting point and you have an end point, and you care about the difference between the two.
Yes.
That's it. For distance, you measure the entire thing. You can go around 100 miles and come back.
Yes.
That is correct. All right. So how does the displacement relate to the velocity? Velocity is really the rate of change of the displacement. So if we first select the reference direction to be the same as the displacement, velocity, and acceleration of a point of interest. So velocity is the rate of change of the distance. Acceleration is the rate of change of the velocity, which is the second derivative of the distance. You all know this from Physics 101. So we have, again, a reference direction and a true direction. When we draw, we show the reference directions, but the true direction can be this red line. But again, this is to the left. So we have the reference direction always drawn with an arrow. But the true direction can be along the same direction or some other direction. So let me give you an example. If I have a function cosine 0.5t, identify the range in which the actual direction is the same as the reference direction. You need the range for t in radians. And then identify the range in which the actual direction is the opposite to the reference direction. So you have t between 0 and 2 pi. Split this t into two parts. Parts in which you have the same direction as the reference direction, and part in which you have opposite direction as to the reference direction. Imagine that the reference direction is to the right. Yes, Faisal?
So if you are going with the same 0 to pi, and the opposite will be from pi to pi.
So you have 0 to pi. Are you sure? How about this? I'll give you 3 minutes. Everybody, please grab a piece of paper and a pen and try to figure this out. And then I'll hear your answers. And by the way, usually in my classes, because now we're going a little bit more mathematical than the first week, I will give exercises on the spot. So please, when you attend the class virtually, have a piece of paper and a pen handy. Okay? Faisal, you wanted to add something to your earlier comment?
No, sorry.
No problem. Abdullah?
Doctor, I didn't understand what's the reference direction.
Okay, the reference direction is the positive direction. Okay?
So what is it in this example?
So you have a function, okay? That function is cosine 0.5t. It can be either positive or negative, right? Because f is between what? Between -1 and 1, correct? So t here, there are some values of t in which f is positive, and there are other values of t in which f is negative. If it's positive, then we call it the same. It's the same direction as the reference direction. The reference direction is the positive direction. Okay.
Okay, I understand now.
Good. All right. Yes, Muhammad.
It's positive from 3 pi over 2 until pi over 2. يعني لو تقسمها 4 الربع الرابع والربع الأول positive، لكن الربع الثاني والثالث negative.
So it's positive from 3 pi.
3 pi over 4, sorry, yes. 3 pi over 4
Uh-huh.
2 pi over 2. Pi over 2.
Just half pi.
Yes. These are positive, but otherwise negative.
Okay. So from 3 pi over 4. So basically, if I have 4 quadrants,
Fourth and the first.
you're referring to this
Yes.
area.
Yes.
Okay. Any other answers? Yes, Mazen.
It is positive when t is between 0 and pi over 2, and
Okay.
from 3 pi over 4, from pi to 3 pi over 4.
So let me use green. So you say it's positive over here. And where else?
And from 3 pi over 4 to, from pi to 3 pi over 4.
You mean here?
Yes.
Okay. Any other answers? Okay, I'll give you 30 seconds and then I will discuss the solution.
بنكتشف إني ما أخذت النص في الاعتبار.
Which half?
اللي في المسألة كوساين هاف تي ما حسبت حساب الهاف.
So what is your answer? Everyone
كانت
has
بالأحمر بس فيها من جديد.
Okay, so what is your solution now?
أو سي.
Okay, I'll wait for it. Yes, Abdullah.
So t should be between 0 and pi, and
Okay.
between 3 pi and 4 pi.
3 pi
For it
and
to
4
be
pi.
in the same direction as the reference direction.
So we're using from 0, we're talking from 0 up to 2 pi. We don't have 3 pi. So maybe you're referring to this area, right? And then the remaining parts are just multiplications of it, and like addition of 2 pi to it. Is this what you mean? The black
No, I
area?
mean that f will be positive in the first and the fourth quarter of the
Quadrant.
yeah.
Okay.
Because
So we
it's cosine.
Okay, so we have the first and the fourth. Okay. Okay. Let's see what the answer is. So remember that we have 0.5t, right? So you're not only applying it to cosine directly, you're actually also considering the 0.5. So from 0 to pi and from 3 pi to 4 pi. This is when you have the reference direction. They're the same as the reference direction, right? So over here. And 3 pi to 4 pi is multiplication, like it's an addition of 2 pi to it. Then you have the opposite direction over here, because you're multiplying by half, right? Because you're multiplying by half, you're not taking it from 0 to pi over 2, let's say, and then from 3 pi over 2 up to 4 pi over up to 2 pi. It changed a little bit because of that positive and negative direction aspect, and because of the 0.5 multiplied to t. So you need to be careful. So because of the change in the argument, because we scaled it by half, that changed the thing. But anyway, the main idea is as follows. The reference direction is the positive direction, and the negative direction is the opposite direction. So if you move opposite to the reference direction, you do the negative, and otherwise you do the positive. Any questions so far? Is it clear? Abdullah, you wanted to say something? Mazen?
Doctor, I don't understand what is the positive direction or the reference direction.
Okay, so this is a function f, right?
Yes.
When f is positive, that's the positive direction. When it's negative, it means it's the negative direction.
Oh, okay. It's clear now.
Yeah, so we're trying to solve for t such that we identify the range for t in which you are in the positive direction, right? The thing is here, the argument 0.5t is between 0 and 2 pi, right? So from 0 up to, so if you multiply by 2, then what happens is that you have 0 t up to 4 pi, right? And then you have, this is the range for t. So you want to split it into two parts in which f is positive, parts in which f is negative. And this is the solution from the knowledge of the cosine function. Is it clear?
Clear.
Good. All right. So we have what's called the reference position. Yes, Sultan.
Doctor, regarding the splitting, we just try in the function like trial and error.
You know the cosine function, and you know the four quadrants, and you know that the cosine is positive in the first and the fourth quadrant, right?
Ah, okay.
Then you multiply it, but then you just scale it. You multiply by 2 because t is multiplied by half. Then you scale appropriately, and you get these regions.
Okay.
So from the knowledge of the cosine function. So yes, you can think of a trial and error, but it's easier than trial and error.
Okay, thank you.
No problem. Yes, Mazen.
Doctor, shouldn't in the answer t should be from 3 pi over 2 instead of 3 pi?
Okay. 0.5t is between 3 pi over 2 and 2 pi. But because t is a scaled quantity of the, so if you have cosine theta, okay, then theta is between 3 pi over 2 and 2 pi. But theta here is actually half t. So you have to multiply by 2 and you get 3 pi to 4 pi.
Oh, okay.
Any other questions? Okay. So let's keep going. So we have what's called the reference position. So we talked about the reference direction. Now we have a reference position. So when you measure a certain distance or displacement, you measure it according to a reference position. The reference position is the zero position of the system. Okay. So we use this wall with these lines as the reference position. So let's say 1 unit to the right here is positive 1. And let's say 2 units to the left here is negative 2. This is 0. Okay? This is the idea. So in our diagrams, we use this symbol for the reference position. Just one line with some smaller lines in a diagonal way. So for both figures, x of t represents the distance from the left side of the body to a fixed wall. Okay? The reference position, x is equal to 0, is usually selected as the equilibrium position. It's the position in which there is no external force. It's like your starting point of the system. You measure everything according to that equilibrium point or the reference point. And usually it is 0, but you can still have another equilibrium. That's not 0, that's fine. But usually we treat it as 0. So what does x minus 3 mean? It means 3 meters away from the equilibrium position in the opposite direction to the reference direction. It's like minus 2 here. Minus 3 is this one. Minus 3. So it's this point. Any questions? Okay. Now we also have a reference direction for the translation and mechanical models. So the reference direction is the direction. The reference direction of the force indicates the positive sense. So you usually take it to the right, but you can still take it to the left. It's up to you. What does F minus 5 newtons mean? It means the force is equal to 5 newtons and its direction is opposite to the shown reference direction. Is it clear? Any questions so far?
It's clear.
All right. So now we have what's called element laws. So we have different mechanical elements in this course, and we need to build mathematical relationships between these elements. So we use element laws, some laws that we use to describe some aspects of these elements. For example, if I have a spring, it must have some coefficient, and we use a linear relationship for the spring. Things like that. So physical devices are represented by one or more idealized elements. Sometimes we need some approximations. Elements for mechanical systems, we use mass, friction, and stiffness. So the friction is represented by a spring, and the stiffness is represented by, let's say, a damper. So mass is defined as the quantity of the matter in an object, and its unit is kilograms. So the sum of forces applied to a body is equal to the rate of change of the momentum. This is Newton's law, right? So the force is equal to ma or m dv dt if the mass is constant. Usually we use constant mass, so it doesn't change with time, so it's just that. So when friction is ignored, we use some wheels. Otherwise, we use these lines or X's to indicate an existence of friction element. So when a body moves on a surface, a friction force is acting in the opposite direction of the motion. Because if the motion is to the right, then the friction is acting to the opposite direction. Because it's not helping you move further to the right. The friction can be linear or non-linear. The linear friction, the viscous friction, is proportional to the difference in the velocities of the two objects. I will continue the discussion on friction and stiffness elements in next class. Okay. For now, I think I'll stop here. We're 7 minutes early, so please use this time to go to Gradescope if you haven't done so already, and to register for an account and make sure that you have access to